Bem-vindos ao nosso espaço, um mergulho profundo nos assuntos mais interessantes de esportes, ciências e temas gerais do momento. Aqui você vai encontrar conteúdo de qualidade, com análises empolgantes e descobertas fascinantes que vão expandir seus horizontes. Nossa missão é trazer informação relevante de forma dinâmica e descontraída. Queremos que você faça parte dessa jornada incrível de conhecimento e diversão. Se gostar do nosso conteúdo, não esqueça de deixar seu like e se inscrever no canal para não perder nenhuma novidade. Ative o sininho também. Aproveite!
If you love science, don't forget to like and subscribe. Beneath our feet lies an ancient, silent record keeper. Quartz is one of the most abundant minerals in Earth's continental crust. Sand on beaches, veins in granite mountains, and grit underfoot are all composed of this simple compound of silicon and oxygen. Yet quartz is far more than mere rock. It possesses a remarkable physical property known as piezoelectricity. When subjected to mechanical pressure, its asymmetrical crystalline structure generates an electric voltage. Conversely, applying an electric field causes the crystal to physically flex. For decades, human technology has exploited this phenomenon in quartz watches, sonar, and microprocessors. But nature was using quartz as an information storage device billions of years before humans built the first microchip. Welcome to the concept of the crustal register. To understand how quartz stores volatile Earth memory, we must peer into its atomic geometry. Quartz crystals lack a center of symmetry. When tectonic forces compress or shear a vein of quartz during deep crustal movements, the internal ions shift. Positive silicon ions and negative oxygen ions move relative to one another, creating microscopic dipole moments. Across a massive geological formation containing millions of tons of quartz, severe stress events, such as earthquakes, subduction strain, or volcanic faulting, build up intense localized electrical potentials. These transient electric fields interact directly with trace impurities and point defects scattered throughout the crystal lattice, such as aluminum or titanium atoms replacing silicon, or vacant lattice sites where atoms are missing. When a subterranean earthquake strikes, the sudden surge of mechanical stress generates a powerful piezoelectric pulse. This pulse energizes free electrons within the rock matrix, knocking them loose and driving them into high-energy trap states created by those lattice defects. Once caught in these quantum traps, the electrons remain locked in place long after the seismic shockwaves have dissipated. In essence, the mechanical energy of the Earth tremor is transduced by piezoelectricity into an electrostatic memory footprint embedded within the mineral itself. The quartz vein becomes a solid-state geological tape recorder, registering the exact intensity and duration of tectonic strain experienced deep inside Earth's crust over millions of years. How do geophysicists read this crustal register? Scientists utilize sophisticated laboratory techniques like electron spin resonance spectroscopy and optically stimulated luminescence. By carefully heating or illuminating quartz samples extracted from deep fault lines, researchers excite those trapped electrons, forcing them to fall back to their ground states. As they drop, the electrons release energy in the form of faint photons of light. The brightness and spectrum of this luminescence directly correlate with the amount of stress energy stored in the crystal lattice over time. This allows geologists to map the magnitude of ancient earthquakes, determine the precise frequency of prehistoric fault slips, and reconstruct the lost stress history of entire mountain ranges. However, this geological memory is described as volatile because it is not entirely permanent. Just as thermal heat can wipe a magnetic hard drive, extreme geothermal heating or intense radiation can clear the electron traps within quartz crystals, resetting the register to zero. If a tectonic plate sinks too deep into the mantle, geothermal heat thermalizes the trapped charges, erasing the previous stress records. But this volatility is precisely what makes quartz so valuable to geoscientists. The reset button provides a clean slate every time a quartz vein undergoes major metamorphic heating, ensuring that the stored data reflects the most recent major tectonic cycle rather than a scrambled accumulation of ancient chaos. By decoding the piezoelectric memory of quartz, researchers are gaining unprecedented insights into seismic hazard assessment. By analyzing the accumulation rate of paleostress signals in quartz rocks along active fault lines, geophysicists can evaluate how much strain energy a fault zone has accumulated since its last major eruption. This provides crucial physical evidence for estimating where and when future catastrophic earthquakes might occur. Beyond Earth, planetary scientists are already eyeing quartz deposits on Mars and the Moon, hoping to read the ancient impact and seismic histories locked inside alien rocks. Quartz is not just rock, it is Earth's living hard drive. For more incredible facts like this, don't forget to subscribe and turn on notifications.